Good afternoon. Welcome back to your favorite class. Rawr! Announcements. Number 1. Simulation 1. Ooh, my dog just passed. Simulation 1 is due on Friday. I had a lot of questions about it in office hours, so that's good. That means people are working on it and kind of taking the bull by the horns and getting after it. That's awesome. If you're having struggles with MATLAB or kind of how this kind of process is working for that simulation, please come see me in my office hours. All right. Number 2, I've posted another homework. That's homework number 4. It will be due next week, Tuesday, and it is on the stuff we're talking about in class this week. So work in energy methods and how those apply to rigid bodies. Lastly, kind of in the future, but not the too distant future, is your next exam for this class, and that is exam number 2. That will be on kinetics, which we did last week, work in energy, which we're doing this week, and impulse and momentum for rigid bodies, which we're going to talk about at the beginning of next week. We're going to have to make that discussion on impulse and momentum a little bit shorter, but that's the way that the cookie crumbles, as Bruce Almighty says. All right. So that's coming in the future. I'm going to make some practice problems for you guys, just like I did for the last exam. So look for those probably this weekend sometime-ish. So you have some additional practice problems if you want to sort of work through those. Okay? Any questions? Now is the time. Otherwise, if there is no further ado, I hate ado, then we can proceed with the lecture. All right, doesn't look like there's any questions, so let's pivot you guys over to the whiteboard, writing pad, whatever you want to call it, electronic pad of awesome. We'll get you over there. You guys like my little my meme today? On the road to success, there are no shortcuts. Okay. I like this particular picture today because we're going to be doing some tough math today. So people that like derivations and complicated math with dot products and integrals and cross products and yada yada yada, today's your kind of day. All right, baby. If you like that sort of stuff and you enjoy derivations and what we're going to talk about today, then good for you, and you should go to graduate school. Rawr. Okay, well, you should all go to graduate school, but especially if you like derivations like the one we're going to do today, definitely go to graduate school. All right. For those of you that don't necessarily like the derivations and crazy complicated math, too bad. You're engineers, you need to be good at math, and you need to be comfortable with complicated math, so buckle up, because we're about to do some. All right. So we'll kind of pick up and review sort of the things we talked about last time, and then get in with our new material. So last time, recall we were doing work in energy methods. And we sort of overlaid the whole discussion yesterday with the overarching equation that we're going to use for this portion of the course, pretty much every problem that we do, and that is conservation of energy. Which is something like T1 plus V1 plus U1 to 2 equals T2 plus V2. So this is the equation you're probably going to write on every single homework problem and exam problem that we do for this portion of the course. And this guy, Sparkleworthy. All right, that's definitely one you should commit to memory. Where we said things like T was kinetic energy, V is potential energy, and U1 to 2 is work of external forces. Forces and or moments. See if I can fit this in. I can expand this guy. All right. That general conservation of energy equation you should have seen before with your particle dynamics class. And the point of what we're doing now is we need to update some of the terms in this particular equation, not just for particles now, but for rigid bodies. I'll say we need to adapt these terms for rigid bodies. All right. You had probably seen them with particles. Hopefully in your 2002 class, you did conservation of energy for particles. And now we need to sort of adapt or upgrade these terms so that we can talk about what they look like for full rigid bodies. All right, so the first one that we talked about was work of external forces and moments. And I gave you the full sort of mathy equation of what the work of external forces and moments were. And that is for a rigid body. We had that the work on an object as it moves from location 1 to location 2 in space is the integral of, as I move from position A1 to position A2, all the forces acting on the object dotted into the path along which the object is moving. So the forces dotted into the path, plus we had this new term now that was the external moments and the work that those do. As I move from angular position A1 to angular position A2, the moments dotted into the angular path that's traversed d theta. This is kind of the very mathy big boy version of this equation, which is a little bit difficult to interpret physically. I don't know about you guys, but as an engineer, I like to physically understand what each one of the terms in an equation means. It like makes me feel more comfortable and make me feel like I sort of understand the world a little bit better when I can look at an equation and say, okay, I physically understand what that is. I physically understand what that is. With this equation, it's kind of difficult, but this is the full three-dimensional mathematical form. There's no Cartesian, cylindrical, spherical coordinate system here. There's no specification to the directionality of each one of these guys. It's just, this is the dot product, this is the integral. It's a very mathematical, but it is the full 3D form. In our class, when we're talking about two-dimensional analysis, which is mostly what we're doing in this class, and if we're sort of containing ourselves to a traditional Cartesian coordinate system, like the IJK coordinate system, we sort of make simplifications to this, which are a little bit easier to understand. So in 2D with Cartesian coordinate system, that's your typical IJK coordinate system. This then kind of chills out a little bit, and it makes it a little easier to understand that if we have external forces in an x direction, that the work of those external forces are the force in that direction integrated along the path from position x1 to x2. Here, same thing in the y direction as we move from position y1 to y2, the force in the y direction dy, plus similarly now with the moment as we move from position theta1 to theta2 of the moment, I'll say acting in z, d theta. That sort of subscript z is a little bit optional, but you get the idea that the moment that we generate in 2 dimensions will be sort of out of plane. Right? So this guy is one that you will probably be using in this class, since we're kind of constraining ourselves to 2D rectangular coordinates. All right, so that's sort of where we left off for that guy. That was the work on a rigid body of external forces and moments. Then we sort of pivoted our discussion, Ross style pivot, to kinetic energy. Which is the variable that we typically use capital T, scalar value, not a vector. And for particles, you probably saw in your 2002 class that the kinetic energy was equal to 1/2 the mass of that particle times the magnitude of the velocity of that particle squared. This was sort of the discount, double check, dollar store version of this equation. And we know that we could reorganize this after our discussion yesterday to be T equals 1/2 the mass of the velocity of our particular particle dotted with the velocity of our particular particle. So remember that this dot product is actually a scalar, so we haven't violated any laws of mathematics, vector math, sort of stuff like that. So this is the more mathematically accurate sound version of the kinetic energy of a particle, and this is one that we're going to utilize in our derivation of the kinetic energy. Now, when we move to rigid bodies, what we're going to do is anticipate what the kinetic energy of each particle that makes up that rigid body is, and then integrate the contributions of all of those individual kinetic energies of all of those little particles on the body to come up with an expression for what is the total kinetic energy of the rigid body. So for rigid bodies, we'll sum contributions of all particles that make up the body. So what that looked like is we had a differential form of the kinetic energy of some random particle P was 1/2 a differential mass multiplied by the velocity of that particular particle dotted with the velocity of that particular particle. So this was a infinitesimally small contribution of the kinetic energy coming from one particle that might make up a collection of particles that we know as a rigid body. So for whole body, we saw that the kinetic energy of this rigid body was equal to integrating over the mass that general form, which was 1/2 dm vp dot vp. And in this situation, we let the velocity of p equal to the velocity of g, which is the velocity of the center of gravity of the object, plus the velocity of p relative to g, where we said that the velocity of any random point on the body vp is comprised of the translational velocity of g and this fixed axis rotation of p about g. All right. So if we let that certain thing happen, then we sort of plugged this in for our VP and foiled this and distributed out. And we ended yesterday's discussion with an expression for the kinetic energy of a rigid body, which looked scary. All right, I'm scared. Okay, and I've been teaching this. All right, but don't be scared. Don't be afraid of math. We can do it. That the kinetic energy of the rigid body is equal to the integral 1/2 dm of, after foiling all of this out, we have the velocity of point g dotted with velocity of point g plus 2 times the velocity of point p relative to point g dotted with the velocity of g plus the velocity of point p relative to g dotted with the velocity of point p relative to point g. And this is about where we left off. I had a question if this particular equation was box-worthy and sparkle-worthy. Not yet. All right, we got to do some work on this bad boy. We're going to simplify it down so that it ain't so crazy, and it'll make a little bit more sense after we work through it. Then it will be box and sparkle-worthy once we get done with today's lecture. Now, each one of these terms, when I look at that, I'm not comfortable. All right, as an engineer, I like to look at a term and say, what is that thing in real life? What is that thing physically? So if I look at this term and I'm like, all right, what is the integral of dm vg dot vg? I don't know. It's confused. I'm confused. It's complicated. I don't know. Or what is this vp relative to g dot vg? I don't know. I'm old. Leave me alone. All right. And what about this guy? I don't know. All right. Well, let's see if we can do some math to these guys and simplify them down. So let's label these as like term number 1, term number 2, and term number 3. what we're going to do today is we're going to work our way through each one of these individual terms, and there's going to be some kind of complicated math and geometric interpretations, but at the end, you'll be left with a physical meaning for each one of these terms that actually sort of makes sense and that you can sort of wrap your mind around for the kinetic energy of a rigid body. All right. So let us be on with it. So here we go, term one. Term number one is the integral in the mass of 1/2 dm vg dot vg. First thing I want to say for this particular term is that recall that the velocity of g, each one of these individual terms, was like the translational component of the velocity of some arbitrary point. So remember back up here, this vg term was the translational velocity of the center of mass. Okay, so all points on the object, random points p, will have this same translational velocity. So remember, if we're talking about translation of an object, all points on that body have the same translational velocity. So what that means is that this vg term is not in any way dependent on where we are on the body or the mass associated with the point of interest. So because of that, vg is translational velocity. All points, same translational velocity. So if we're looking at this integral, which is the integral of these velocities at all points in the body, it doesn't matter where we are in the body. So we can just pull that term out. It is not a function of where we are in the body or any particular mass of the body. So regardless of the mass, regardless of the location, doesn't matter. So the point is that we can pull this guy out of this particular equation, and also we can pull the 1/2 out because obviously is not a function of mass because it's a constant, and we'll be left with a term that looks something like 1/2 vg dot vg multiplied by the integral on the mass of dm. Well, this we can simplify again. Notice here that the integral on the mass of all the differential masses is just the total mass of the body. This is m, which is total mass of rigid body. Right? First fundamental theorem of calculus. Rawr! Okay, it is useful. We also saw this previously. The velocity of a vector dotted with itself is just the magnitude of that velocity squared. So this here is the magnitude of the velocity of the vector g squared. All right, we saw that previously. We saw that yesterday. So hopefully we're comfortable with that. So what that means is term number one simplifies to what is 1/2 the mass of the object times the magnitude of the velocity of the center of gravity of the object squared. Important, this is velocity of center of mass. Very important, center of mass, right? Not the velocity of some random point on the body. It's the velocity of the center of mass. Very important. Okay, this looks very similar to what you did in 2002, which is 1/2 mv squared. The distinction here is that this is specifically the velocity at the center of gravity. So this term represents the kinetic energy associated with translational motion. Bam! All right, that's term number one. We still got 2 more to go. So don't be getting complacent. All right, we got 2 more. Next on the docket, this guy right here. 2 times the velocity of p relative to g dotted with the velocity of g. Oh, my head hurts. All right. I'm old. All right. So term number 2, and I'm going to bring the integral and everything associated with it. So pretend that I distributed all this stuff to this particular term. All right. Term number 2 is we have the integral on the mass, 1/2 dm of this 2 velocity of p relative to g dotted with velocity of g. Okay. This one, complicated. All right. This is by far the hardest term to deal with. And we're going to do some geometric interpretation of this particular guy. So this requires a little bit of drawing, a little bit of sort of understanding what the dot product is, understanding what VP relative to G is. You really sort of have to understand what each one of these terms is and what the mathematics associated with this particular operation is. So I'll say this requires some geometric interpretation. Now, I'm going to draw a picture here of a rigid body, and I'm going to make it pretty big because I'm going to put a bunch of stuff on it. So if you're taking notes by hand and you also want to sort of draw this picture, make sure you give yourself a good amount of space. All right. So here we have big mechanics potato. Rawr, big potato. All right. At the center of that potato is the center of gravity, G. All right. We're going to say here that the center of gravity, G, has velocity. And it acts along unit vector, which is defined by lambda for the velocity of G is the velocity of G normalized by the magnitude of the velocity of G. All right, so this is just a unit vector in the direction of the velocity. Well, that's pretty easy to understand. Let's say that this guy has some velocity, and I'll just sort of draw it in a random orientation. Here is the velocity of point G, and there's a unit vector associated with that particular velocity of point G. And that unit vector here is lambda in the direction of the velocity of G. Pretty easy to understand. All right. This is sort of the foundation. We're interested in another point on this object, some random arbitrary point. And let's call that point up here. Let's call it point P. All right. Now I'm interested in the velocity of P relative to G. Velocity of P relative to G. Well, if we have no angular velocity, then this term will be 0. So remember that the velocity of P relative to G is something like angular velocity crossed with the position vector locating P from G. So let's put some angular velocity on this particular body. Let's say that it's rotating with some angular velocity omega in this general direction. And so then the velocity of P relative to G is like the fixed axis rotation of P about G. So that means we have a vector that defines P from G, RPG, useful in military world, but this is a different RPG. And because this guy is spinning around, we're going to have a perpendicular to this, which is the velocity of P relative to G. All right, which we know has this general definition here. All right, and this guy is perpendicular to this guy. All right. Now it's time for us to turn our attention toward the dot product here. So we have this dot product up here. It's the velocity of P with respect to G dotted into the vector defined by VG. So if we want to take the dot product of the vector P relative to G and dot it into the direction associated with the velocity of G, then we want the projection of this particular vector onto this particular vector. That's sort of how the dot product works, right? You dot a certain vector into another vector, you get a scalar value, which is the magnitude of the projection of that vector along that particular direction. So if I project this vector down into this general velocity of g, I end up with a vector that looks like this, where here, I'll do it over here, give myself a little space. Here, this is the dot of the velocity of p relative to g dotted with the velocity of g, and this particular vector happens to be along the unit vector which defines v from g. So that is that vector that we have created. It is the projection of that velocity of point p relative to g onto the vector defined by the velocity of g. All right. So a little bit complicated, a little bit hairy there, but I think so far we're okay. Now, what is this integral then? All right. Well, this integral here is the contribution of all of the points P on the body with this general projection added together. So what that means is that there are points that exist all over this body. There's one here, 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 so on and so forth, that are all going to have this same general idea, is that they're going to have some velocity relative to the center of gravity that sort of like looks like this. And then we can project their vectors onto the velocity of g equally and create some projected vector along that particular direction. All right. More specifically, I'll say that because we're at the center of gravity, right? We're located here at the center of gravity, and we've defined point P from the center of gravity. That because of the definition of the center of gravity, for every point P that exists with a mass of m away from point G, there is another point P prime that's like the mirror of that. All right, it's like regular link and dark link. Okay, it's good guys, bad guys. It's yin and yang. All right, so we got this point P up here, and there is an opposite of that, which on the back side here is something like P prime. All right, here this is located at position vector P prime relative to G, and this will have velocity relative to point G here of velocity of P prime relative to G. Now if we notice that we can also take the projection of that vector onto the unit vector which defines the velocity of G, we can project this guy backwards as well and have a similar looking vector which points in the opposite direction. So this guy here, this is the velocity of P relative to G dotted with the velocity of G in the direction of the velocity of G. What's the point? The point is, for every single point P that exists, there is this dot product of Vp relative to G dotted with Vg. And because there is this yin-yang relationship of every single point that exists, there is an opposite point that exists that will have a velocity that is equal and opposite in magnitude to the current position that I'm in. Everything is just going to cancel itself out. So let's write that in English. So since we are at the center of mass, and there exists this sort of yin and yang P prime points, right? Each point P has a counterpoint P prime with the following relationship, that the velocity of point P relative to point G is equal to the negative velocity of point P relative to point G. And that's what we see generally with like this vector here and this vector here. They're basically equal and opposite in direction, all right? They're equal and opposite vectors. So because of that, when we add the contributions of all of these dot products, which is like this vector and this vector projected into the direction of G, there'll always be these equal and opposite pairs that work to cancel each other out. So the integral on the mass of this particular dot product is 0. That's the whole point of that long discussion. Hopefully you can geometrically understand why that is now that I've sort of drawn it out quite a bit and shown what this really is. But it kind of has to do with balancing out angular momentum and fixed axis rotation about a point when that particular point is the center of gravity, so on and so forth. So all that rigmarole just to say that this particular term, term 2 here, is equal to 0. We saw here that this term was 1/2 m vg squared. All right, so we're making our way through. Slow and steady wins the race. That's what the tortoise says to the hare. All right. Stay hydrated. Rawr. Usually coffee, but today I got water. Trying to be healthier. So that's term 2. Finally, term 3. This guy here, velocity of p relative to g, dotted with velocity p relative to g, and I gotta, again, take all this stuff with it. All right. Okay, so that's my third term. Now, the third term requires a little bit of information that we talked about in our kinetics lecture. Okay, so we'll sort of build it as we go. But one thing that we know about the velocity of p relative to g is that it can be written in terms of angular velocity and position vector. So remember, back from, honestly, week number 1, is that the velocity of any point on the body relative to some fixed point, which we're sort of assuming here with vp relative to g, is the angular velocity of that body crossed with the position vector that locates that point on that body relative to the fixed point g. Right? So we're going to leverage this in this derivation, but I'm only going to plug it into one of our components. So move down here. We'll have this as the mass, 1/2 dm of, I'm only going to plug in for term number 1. So this will be omega cross position vector of p relative to g, dotted with the velocity of p relative to g. All right. Now I'm going to leverage an identity for cross and dot products. That you may have seen when you did the triple product or when you did the projection of moments onto a line in your statics class. You may have seen this identity, maybe not. And that is that if you have some vector A crossed with some vector B, dotted with some other vector C, that is equivalent to the vector A dotted with the vector B cross the vector C. So this is an identity for cross products. Now we're going to leverage that in this particular portion of the equation. All right. So we're going to end up with something like omega dot RPG cross VPG. All right. So simplifying, integral in the mass, 1/2 dm of, now leveraging my identity, omega dotted with, what is RPG? Careful. Duck, RPG. Dotted, crossed with the velocity of p relative to g. All right. So here we are. Now we have to go back and think about our angular momentum discussion that we got into when we did kinetics. And that is that the angular momentum of a particular point is the position of that point crossed with the velocity of that particular point. So we'll recall also that the angular momentum of some point relative to some other point, let's say the angular momentum of P relative to G, is the position vector locating P relative to G crossed with the velocity of that particular point. All right. That's not exactly the case because we did have a little m hanging out here for the linear momentum. So it's m vp, but this is close. I'll say almost is the case of this. But we'll say here that we can simplify this and write this as the integral on the mass. I'll take the 1/2 out now on the left-hand side. And this will be omega dotted with, and I'm free to put this dm wherever I want, let's substitute in our rpg cross dm vp. All right, now we're starting to look a little bit closer to what this is. All right, so now when I come down here, I can make some further assumptions. One of those assumptions I need to make is I have a lot of recalling, so I don't know how good your guys' memory is. I'm getting old. My memory is a little lackluster. But all points on the rigid body have the same angular momentum. Angular velocity omega. So we've shown this mathematically before when we were working in week number 2. Or was that week number 3? Week number 2 that we had together. All right. So all said and done, we can take that omega out. We have omega dotted with integral on the mass of what here would be the partial or the infinitesimal contribution of all the angular momentum of all the individual components P relative to G. That is this term here. All right. Well, the integral on the mass of all the differential contributions of the angular momentum is just the angular momentum of the object P relative to G, which we know is Ig omega. So in closing, this last term is 1/2 omega dotted with Ig omega. Okay, this is term number 3. It looks very similar to 1/2 m v g dot v g, which we saw before. This term here is the kinetic energy associated with angular motion. All right. The dollar store version is 1/2 Ig omega squared. That's your dollar store version. All right, so this is the full 3D version. The dollar store version, probably good enough for us. All right, since we're working in 2 dimensions, we're working in rectangular coordinates, that's probably good enough for us. So to sort of round out the lecture today, let's kind of bring this to a close. All right, we started with the kinetic energy of this full rigid body equal to this crazy integral, 1/2 dm of what is the velocity of g dotted with the velocity of g plus 2 times the velocity of p relative to g dotted with the velocity of g plus velocity of p relative to g dotted with velocity of p relative to g. When we first looked at that, I didn't know what any of that meant physically. I don't know what those things are. I'm old. Leave me alone. All right. However, we've worked through them and manipulated them to a condition where we could understand physically what each one of these things is. All right. So when we simplified these things down, we saw that this term here was simply 1/2 the mass of the object times the velocity of the center of gravity of this object. So I'll just write this as, Vg squared, specifically the velocity of the center of gravity, okay? Plus, we saw this entire term here was equal to 0, plus this term here, which we see as 1/2 Ig omega squared, where Ig is the mass moment of inertia of our object about the center of gravity, and omega is the angular velocity of the piece. So in closing, we have that the kinetic energy for a rigid body in any particular condition is 1/2 mass of the rigid body times the velocity of the center of gravity of that rigid body squared, plus 1/2 mass moment of inertia of that object about its center of mass, multiplied by the angular velocity of that object squared. Sparkle time. There you go, Alec, just for you. Rawr! Sparkles! This term here, kinetic energy of linear motion. This term here, kinetic energy of angular motion. It would make sense that the kinetic energy of these two, of rigid bodies, is sort of separated into these two different things, okay? If I have an object, okay, here's my cell phone. Call me anytime, day or night. Just kidding, don't do that. Here's my cell phone. It could translate through the world, okay? If I just threw this at the wall with no spin on it, it'd be moving at the wall, and it would have some kinetic energy associated with the linear motion of this object, okay? As it moves through space, it has this kinetic energy associated with it, which is like the kinetic energy of a particle, which is 1/2 mv squared, all right? I could also think about like spinning this on my finger. I'm not going to do it right now, but maybe if you guys are bold and risky, you can try it at home. I could also spin this on my finger and understand it. The faster and faster I spin it on my finger, the more and more energy it will have. Okay, so there's energy associated with how fast it spins. So even though it's not necessarily moving through the space of, in a linear direction, it still has angular energy associated with that. And we see that that angular energy is contained in like this 1/2 Ig omega squared term. Okay, so the more mass it has, right, the larger the mass moment of inertia, and the more angular velocity it has, the more potential energy, kinetic energy it will have. All right, so almost done defining all of our terms for conservation of angular momentum. We've done work of external forces and moments. We've done work of kinetic energy. Tomorrow we'll finish up with the potential energy terms, and then we'll do practice problems probably starting in on tomorrow. So that's going to be it for today. I'll hang out for questions and say thank you for coming. Rar. Thanks, Prof. You're welcome, Jess. Thanks for coming. Rar. Can we get an MBA instead? Well, maybe, David. It's not too late. Yeah, I like that. You got to put my face on there.